Hello, this is the fifth video of the fourth Graphs and Networks series on route inspection and the travelling salesperson problem for OCR Discrete Further Mathematics. And we will look at a method to find a lower bound. In the previous video, we looked at finding the smallest upper bound that we could. In this video, we're going to concentrate on finding the lower bound, and we note that it needs to be the largest lower bound. So the greatest lower bound is nearest to the optimal solution, but it probably does not quite solve the problem, in that the lower bound won't be a Hamiltonian cycle, but it should start and end at the same vertex and visit every other node once. In previous series, we have looked at the idea of a minimum spanning tree and finding a minimum connector to connect vertices with a least weight solution. To find the lower bound then, we choose a vertex, which you can call the starting vertex, and then delete this vertex and all its edges. We then use Kruskal or Prim's algorithm to find a minimum connector or minimum spanning tree for the remaining network. We could call this a residual minimum spanning tree or RMST. Then we need to add back in the starting vertex with the two smallest weight deleted edges or arcs. So we note we've got a minimum spanning tree and then two arcs adding back in that starting vertex, and this is unlikely to form a Hamiltonian cycle. So using the same example as in the previous video when we found an upper bound, let us now look for a lower bound. Initially we're going to remove A, and this then leaves us with B, C, D and E. I'm going to use Kruskal's algorithm to remind you of how that works. So I'm going to look at that whole network and start with the smallest arc, and this is BE at 7. The next smallest arc will be ED at 8, noting that Kruskal's chaotic and I don't have to connect this minimum spanning tree at this point, it just happens to be the next smallest arc. The next one is BC at 9, given that I've removed A, so I can't use this arc here. I've then got a minimum spanning tree for those nodes BC, DE, and the weight of that is 24. I'm going to now add back A, and I want to choose the two smallest arcs connected to A to do this. Well, looking there, that's that 8 between A and B and the 9 between A and E. So I'm going to add that 8 and 9 to 24. And this will give me a total of 41 as a potential lower bound. Let's see what happens if we do the same process but remove B and all the arcs connected to B. So I'm left with A, C, D, E. And this time I think I'll use Prim's algorithm, because it really doesn't matter whether we use Prim or Kruskal to get our minimum spanning tree. So I'll choose to start at vertex A. So the smallest arc from A, given that B's been removed, is AE at 9. Followed by, given that E is now connected, I can look at arcs coming out of A or E, and that will be ED at 8. And then I need to connect C, and the smallest arc connecting into C that I can use is AC at 13. These total 30, and so now I need to think about adding back in B. I'm going to choose the two smallest arcs to add B back in, and that will be the 8 leading to A and the 7 leading to E. So if I add that 8 and the 7 to the 30, I would get a potential lower bound of 45. So then, to find a lower bound, we have used steps 1 to 3 for both A and B, and we can see that we get different values of lower bound. So we will extend steps 1 to 3 by realizing that we should repeat that process, deleting a different vertex from the network each time. And then, when we have n options for a network of n nodes to choose between, we will choose the greatest lower bound. So the work we did, we got that total of 41 when we started with A and 45 when we started with B. And we can see that whether we start with B or C, 45 is the greatest lower bound that we can get for this particular network. And therefore we would choose to state that the lower bound is 45. Remember that the minimum spanning tree that each of those options would give us, with the removed vertex added back in with the two smallest arcs, is probably not a Hamiltonian cycle. If they were at all, they would be an optimal solution, and then you would also find that the lower bound equaled the upper bound. Hence, with the work in the previous video and this video, we now know that the optimal solution for the travelling salesperson problem for this particular network is such that we have that lower bound of 45, and the optimal solution must lie between that and also be less than or equal to 48. In the next video, we consider further use of techniques to improve on our solution for the travelling salesperson problem.